Bismillahirrahmanirrahim. Assalamu alaikum, dear students. This is our next problem. Problem number 30. Okay. Fluid mechanics, problem number 30. As usual, we first come towards our statement of the problem. Okay. What is the average density of the sun? Dear students, here we will need a table in which data regarding sun, earth, moon, etc. will be given. Okay. Part B, what is the average density of a neutron star that has the same mass as the sun but a radius of only 20.0 kilometer, that is 20,000 meter. Okay, because we are following MKS system, we will convert this kilometer into meter. Okay, so dear students, first we move to table, from where we will see some required data to be used in this problem. Okay, this is the table. Okay, the sun, earth and the moon. Okay, sun, earth, moon, mean radius, mean density. Okay, so we see, yeah, this is okay. Dear students, sun, mass of sun is 1.9 into 10 raised to the power 30 kg. Okay, mass of sun is 1.99 into 10 raised to the power 30 kilogram. Mean radius of sun is 6.96 into 10 raised to the power 8 meter. Okay, mean density of sun is 1410 kilogram per meter cube. Okay, so dear students, we will use these three values in this problem. Okay, next in this table, these values for earth and moon are also given. Okay, so now we move on to solution of our problem. Okay, solution. First, this problem has two parts A and B. So definitely we will first start part A. Okay, let mass of sun equal to m sun, where sun is written as a subscript of m, is equal to 1.99 into 10 raised to the power 30 kilogram. C table. Okay, we have already seen this table, so matter is quite clear. Okay, moreover, radius of sun is equal to r sun, where sun is written as a subscript of r, is equal to 6.96 into 10 raised to the power 8 meter. C table, we have already seen this table. Okay, similarly, density of earth is equal to rho earth, where earth is written as a subscript of rho. Okay, is equal to 5.52 into 10 raised to the power 3 kilogram per meter cube. C table, we have already seen this table. Okay, so dear students, we have taken all these three values from the table which we have shown a little earlier. Okay, dear students, this symbol rho which it denotes density is lowercase. Okay, we can also write it as capital P, but then in that case that capital P will be assumed as a capital case of symbol of rho. Okay, but usually capital case, that is a capital P, is not used, and this symbol, that is rho, lowercase, is usually used. Okay, now we move on to next part of this problem's solution. Okay, we know that volume of a rectangular solid is equal to length into width into height. Volume of a sphere is equal to 4 by 3 pi r cube, where r is radius of the sphere. Volume of a cylinder is equal to pi r square h. Volume of a cone is equal to 1 by 3 pi r square h. Okay, dear students, actually volume formula for calculating volume differs according to different geometrical shape. Okay, so as a reference we have shown this formula for 4 different geometrical shapes. Okay, now we move on to next part of the solution of this problem. And this part is again in the same manner as our previous problems of this topic, that is fluid mechanics. Okay, density is mass per unit volume. If a mass m of homogeneous material has a volume V, capital V, then its density rho is given by rho equal to m over V, equation number 1. This implies that here in this case this equation will take the form as density of sun, where sun is written as a subscript of rho. Okay, density of sun is equal to mass of sun over volume of sun. Okay, and we have already shown values of these two. Dear students, here mass of sun is this 1.99 into 10 raised to the power 30 kilogram, which we have shown in the table. Okay, moreover, formula for volume of the sun is 4 by 3 pi r sun cube. We once again move to this. Okay, 4 by 3 pi r cube. Volume of a sphere 4 by 3 pi r cube. 4 by 3 pi r cube. Here instead of simply r, we have taken r sun, where sun is written as a subscript of r. Oh, okay. So dear students, in the next step we have put further values. Okay, because here mass of sun was already put. In the next step, what we have done, we have put the value of pi, which is equal to 3.14, and we have sometimes mentioned that decimal representation of pi is non-repeating, non-terminating, it goes endlessly, but usually we restrict our decimal representation to only 2 decimal places. Okay. Similarly, radius of sun is also given in that table. Okay, so in this step we have just put 2 further values. Okay, value of pi and value of r sun. Okay, in the next step we have just simplified this calculation. Okay, kilogram per meter cube. Okay, further we have in the next step we have more simplified this. Okay, dear students, actually here 10 raised to the power 24 will be subtracted from 30, so 10 raised to the power 6 will be left in the numerator, and these 2 values after having been divided will become 0.0014. Okay, so this value alternatively becomes equal to 1400 kilogram per meter cube. That is to say, density of sun Okay, rho sun, where sun is written as a subscript of rho, it can again be written as 1.4 into 10 raised to the power 3 kilogram per meter cube, but that is just a matter of discretion. It is not compulsory. Our solution is quite complete. Okay, now we move to part B. Okay, now dear students, density of neutron star is equal to mass of sun, which is equal to the mass of neutron star. Okay, this equality is given in the statement that mass of neutron star is equal to mass of sun. And mass of sun is given in the table which we have shown in the earlier part of this video. Okay, so density of neutron star, that is rho ns, where ns is written as a subscript of rho, is equal to mass of sun or mass of neutron star. Okay, because both are equal, divided by volume of neutron star. Okay, so here dear students, here we have put the value of m sun. Okay, because mass of neutron star is equal to mass of sun. Okay, so we have used this value from table which we have shown in the earlier part of this problem solution. Okay, moreover, for volume we have again used the same formula, that is 4 by 3 pi r ns cube. Okay, here in place of r sun we have written rns, radius of neutron star raised to the power 3, that is to say cube. Okay, in the next step again we have used the value of pi equal to 3.14 and radius of rns, which is given in the statement, which was 20 kilometer, and we are here concerned with meter, so we have converted 20 kilometer into 20,000 meter. Okay, in the next step we have just simplified this calculation. Okay, quite simple. Here dear students, 10 raised to the power 12 will be subtracted from 10 raised to the power 30, and hence 10 raised to the power 18 will be left, and this thing will result in this. Okay, because if 5.97 is divided by 10, then it becomes 0.597, but when it is divided by 100, then it becomes 0.0597. Okay, so density of neutron star has become equal to 0.059 into 10 raised to the power 18 kilogram per meter cube. It can alternatively be written as 5.9 into 10 raised to the power 16 kilogram per meter cube. Okay, this is just a matter of discretion. We are not bound to do this. Okay, to this extent our solution is complete. Okay, that is to say, density of neutron star rho ns is equal to 0.059 into 10 raised to the power 18 kilogram per meter cube. Okay, to this extent our problem has been solved 100%. However, as a matter of discretion, we have converted this value in some different shape, in which 10 raised to the power 18 has been converted into 10 raised to the power 16, and 0.059 has been converted into 5.9. Okay, dear students, now we are going to compare two densities. Okay, and if difference is very much, then we will say that neutron star is dense very much than earth. Okay, it is to be noted that density of neutron star, that is rho ns, where ns is written as a subscript of rho, is equal to 5.9 into 10 raised to the power 16 kilogram per meter cube, and density of earth, that is rho earth, where earth is written as a subscript of rho, is equal to 5.52 into 10 raised to the power 3 kilogram per meter cube. This implies that density of neutron star versus density of earth indicates that neutron star is extremely dense. Dear students, how we have reached this conclusion? We have reached this conclusion that because density of neutron star involves the power 10 raised to the power 16, while density of earth is only 10 raised to the power 3. Okay, so 10 raised to the power 3 and 10 raised to the power 16, there is a very huge difference between these two quantities. Okay, because this is kilo, then it will become million or mega, then it will become giga, then it will become perhaps tera or next unit, which will be 10 raised to the power 12, and then it will become 10 raised to the power 15. That value will again have some different name. Okay, so we can assume that we can conclude that density of neutron star is at least 5 times greater than the density of earth. So this thing indicates that neutron star is extremely dense, and this is the end of our module. This table, we have already shown this table. Okay, no need for further explanation. Now we move to reference. Okay, reference book is Sears and Zeeman Skies, University Physics with Modern Physics. Authors are Hug D. Young, Roger A. Friedman, A. Lavisford. Publisher is Pearson, and its 14th edition, having been published in 2016, or 15th edition, having been published in 2020. Has been adopted or followed, and here chapter number 12 under title Fluid Mechanics is our concerned chapter, and this problem is enumerated at serial number 6 of the exercise given at the end of this chapter, and this is the end of our problem. Okay.